Here's a quick lesson on units, unit conversion, and dimensional analysis. Units are important because each physical quantity in physics is a measurement, and of course measurements have units. We have the concept of the physical quantity associated with some sort of measuring unit of that. Okay, so it's an important property of each of the physical quantities that we'll study, and also it is something that we will be using in problem solving, not only to help us set up equations, but also to see if our equations are correct or if our answers make sense. So units can be used in different ways. So we'll not only need to know the units, we'll need to know how to convert them and also how to use them with dimensional analysis to check our answers. So the fundamental units, the physical quantities have SI units, the fundamental ones: time, length, mass, and charge. Seconds, and each of one of the units has a shorthand representation. Seconds is S, meters, kilograms, and coulombs. And those are the fundamental physical quantities. All other units, interestingly enough, are combinations of the above quantities. For instance, force, and this is just a few examples I chose. Force is measured in newtons. The standard is newtons, which is a kilogram times meters per second squared. So you can see that these three fundamental units are combined in order to create the force unit. Energy is very similar. The joule is a kilogram meter squared per second squared. Current, amps, is coulombs per second. And you can see all of those are combinations of those four fundamental ones. Magnetic field, a Tesla, is the international standard unit for the magnetic field. It's newtons per coulomb per times meters per second. So very interesting equation. And we can see what newtons are up here. If we wanted to reduce the units, we could take what we know about the newtons and plug it in here, and we could reduce the units in different ways. And so those are the fundamental units. What we will need to know for units is to do a unit conversion. Often we will not measure in the same scale or a system of units as what we may do calculations in. Okay, that happens. We may need to translate our work to another person and need to switch systems. And so we're transforming a value expressed in one type of unit to another value of target unit. So we do this by using conversion factors, which are ratios relating equal quantities of different units. So for instance, 1 inch equals 2.54 centimeters exactly. Very interesting, right? And you can see for other concepts here, we have time, energy, pressure, mass, an atomic mass unit. You can see that there's different conversion factors here. And we're going to use these conversion factors in order to convert from one scale of unit to another. How do we do this? I'm going to anchor you with the ladder method. Unit conversion with the ladder method is a reliable method for doing unit conversion. And the key to this is using conversion factors to multiply by factors of 1. And what do I mean by factors of 1? So for instance, we have the conversion factor 1 mile equals 1.609 kilometers. That's the conversion rate, right? The factor there, okay? So that's true. Depending on the situation, if we want to convert from miles to kilometers or kilometers to miles, we can use a version of this equation. We can manipulate it in order to be a factor of 1. So for instance, if I divide by 1.609 kilometers on both sides of this equation, 1.609 kilometers, on this side it reduces to 1. And on the left side, I'm left with this ratio, right? That's what we were saying, ratios. So I end up with this ratio of 1 unit to another, which is actually a factor of 1. And what we know about factors of 1 is anything multiplied by 1 is still the same thing. So I can multiply by these factors of units and not fundamentally affect the answer, but convert from one system to another. Okay, so that's the idea for unit conversion. So my example here, I have a student ran 3.10 miles. How many centimeters did they run? probably a lot. A centimeter is a lot smaller than a mile. And so I'm thinking that, and this is part of my problem solving, I'm thinking ahead, like I want a really large number. Makes sense. I don't know how much bigger, but I want a really large number. It says, give your answer in scientific notation. Well, that makes sense. If I have a really large number, it'll be better expressed in scientific notation. So here's how to do this. I'm going to take 3.10 miles. And I have the conversion factor up here. I want to go from miles to centimeters. So I'll put this down at the end. I want to get to centimeters, which is in the metric system, and I'm in the British system. So I need this conversion factor, and that's why I put it up here, the conversion factor from miles to kilometers. If I get to kilometers, I can get to centimeters, because I know 1 kilometer is 1,000 meters, and I know 1 meter is 100 centimeters. So I can get from kilometers to centimeters, and I can also get from miles to kilometers. So that's sort of like the bigger picture strategy for solving this. Okay, so how do I use factors of 1? And this is what makes it the ladder method. So I'm just going to draw a long line across here, and I'm going to put the first rung of my ladder. Okay, and if I put rungs along here, it'll be a sideways ladder. It's like lying on its side, and the steps go this way. Okay, so 3.10 miles. I want to convert from miles to kilometers, and I know how fractions work. If I put a factor of miles down in the denominator, I can see that the miles on top would cancel with the miles in the denominator. So when I look at my conversion factors of 1, right, here's my conversion factor. 1 mile equals this many kilometers, right? But it equals 2 versions of 1, right? One over the other. They're both a factor of 1. So what I do is I identify if I want to cancel, if I want to convert from miles, which is in the numerator, I'm going to have to cancel it, which means I'm going to have to put a term of miles in the denominator. And when I look at my conversion factors, this value, this ratio here, has miles in the denominator. So this is going to be the factor of 1 that I'm going to multiply by in order to convert from miles to kilometers. And just to finish this thought, I'm going to cancel the miles here, and the only units left over are kilometers right now. Okay, I'm not done yet. I still need to get to centimeters, right? Those are my target units, and that's what my tip is here. Keep the target units in mind. Once the ladder is set up, cross out canceling units. So that's what this is. Cross out canceling units to be sure you use the right number and versions of factors of 1. So for instance, if I put this in here wrong, if I did miles over kilometers rather than kilometers over miles, the miles wouldn't cancel, right? They would multiply together. I would know that I didn't do the conversion correctly. Okay, so we're in kilometers. Let's go to meters. 1 kilometer is 1,000 meters. I want to get rid of kilometers, which means I need to put a kilometer in the denominator, which means that 1,000 meters goes in the numerator. And you can see that the kilometers will cancel with the kilometers. I'm left with meters. I can also say that 1 meter is 100 centimeters. And so this is our ladder for the problem. I'm going to finish this out, canceling units. Let's see. This kilometer cancels with this kilometer, and I'm left with meters. And then this meter cancels with this meter, and I'm left with centimeters, which is exactly what I wanted, to get from miles to centimeters. All of the other units canceled in this multiplication. So I'll end up with centimeters. When I do this, when I multiply through, you can plug this into your calculator. You get 498,790. Very nice number. And we need to put this in scientific notation. Remember, it says put in scientific notation. I'm going to say this is 4.99. I'm going to note that there's 3 significant figures here. 3.10. There's 3 significant figures here, so I'm going to have 3 significant figures in my answer. I have 4.99 times 10 to the 5th centimeters. I would like to have that much money in my bank account, right? Times 10 to the 5th, take it, right? So that's how you do unit conversion with the ladder method. Not too bad. Not too bad at all. Let's practice a little bit more. Let's do this first one. It says the speed of sound is measured to be 342 meters on a certain day. It depends on temperature, density of the air, etc. What is this in kilometers per hour? So we're going to have to go from meters per second to kilometers per hour. Okay, so we're going to set up this ladder. I'm going to note that I have meters per second to begin with. So in this first rung here, I'm going to put meters on top and 1 second on the bottom. Does that make sense there? Meters per 1 second. Okay. I'm going to extend my line over and put my rung in. And I want to go to kilometers per hour. So then I ask myself, do I want to deal with the length first or do I want to deal with time first? Let's deal with the length first. Okay. So I know that there are 1,000 meters in 1 kilometer. So I dealt with the length. What else do I know? I want to go from seconds to hours. So I know that, let's do this. There's 60 seconds in 1 minute. And then there's 60 minutes in 1 hour. Now, when I was going through this, and hopefully that's what you were doing in your mind as well, is whenever I got a unit here, right? I got meters. They was able to cancel them out and have them a leftover unit. And when I did this with time, I noticed that I had second in the denominator, which means that I needed to put second in the numerator and have minute in the denominator. And I did that game twice. Here's minute and minute, so I could have hour, and the seconds and seconds cancel out as well. So when I look at the units left over, I have kilometers per hour, and that was the target units I was going for. So in order to convert this, let's see, I take 342, multiply by 60, multiply by 60 again, and divide by 1,000. 342 times 60 divide by 1,000. I've already determined that it's kilometers per hour, so I'm not going to worry too much about putting units in that step. And when you calculate this, it turns out to be, it's sound. It can go pretty far in 1 hour, right? How many kilometers would it go in 1 hour? So this is the value. You can plug this through your calculator if you like. 1,231.2 kilometers per hour. I use HR. Some books use H. I suppose miles per hour is like that, so it's just an H. But sometimes I use HR. It depends on your teacher, I think, is what goes on there. So that's the answer. Here's another one. It's a little bit odd, a little bit different, and that's why I chose it, right? It's, can you do novel problems? That's the idea. When you see a problem with a concept, can you do it even though it looks like something that you've never done before? Can you use the fundamental principles in this new context? And that shows that you really understand the principles. So, Daisy Bell bought 15 acres of land and built a house on 2 acres. Daisy wants to raise sheep. If it takes 1/8 of a hectare, okay, whatever that is, a hectare, to raise 1 sheep, how many sheep can be raised on the remaining land? Okay, so it looks like we have 13 acres to raise sheep, right? She bought 15, 2's being used for something else. So there's 13 acres to be used for raising sheep. Okay, so we want to know how many sheep can be raised on the remaining land. Okay, so we're going to convert from acres to number of sheep. Pretty interesting, right? And they tell us here 1/8 of a hectare to raise 1 sheep. So to me, that is a conversion factor. 1/8 of a hectare equals 1 sheep. Okay. So that gets me to number of sheep, and I know that a hectare is an area of land, just like an acre is an area of land. An acre. So the conversion factor, there must be a conversion factor between acres and hectares, and there is. You can look this up wherever you want to look it up, but I can tell you here 1 hectare equals 2.471052 acres. So you may pause for a moment and see if you can answer this on your own. I itch my nose because I need to itch my nose. Maybe somebody's talking about me. Okay. All right, so you had a minute to try this on your own. We're converting from acres to sheep, and I gave you some conversion factors here. It seems like if I want to get to sheep, I have to deal with the acres first. And so in order to cancel out acres in the numerator, I'm going to have to put acres on the denominator, and that means that hectares will have to be on the top in the numerator, hectare. And I'll put these numbers in here. 1 hectare is equivalent to 2.471052 acres. Okay. Now that I'm converted to hectares, I can get to sheep because I know 1/8 of a hectare equals 1 sheep. So if I have hectares in the numerator, I'm going to have to put a hectare down here. And that means that sheep will end up in the numerator, which is what I want. It's what I expect because the number of sheep is what I'm going for. Those are my target units. So I know that 1/8 of a hectare is worth 1 sheep, and I can convert from acres to sheep. Acres and acres cancel there, a hectare and a hectare cancel there, and the only units left over are sheep. When you multiply this through, you take 13 and divide by that and divide by that, you get 42 sheeps. And that is the number of sheep that Daisy Bell would be able to raise on her 13 acres. Let's do one more. I chose this because of dimensions. And I mentioned this on the previous slide, and I'll go back to it just to highlight it. When units are squared or cubed, notice that down here, when units are squared or cubed, you have to square or cube the conversion factor too, okay? I chose a problem that has volume in it so that we can get used to doing conversion factors with powers of our units. Find the volume in liters of a sphere with a radius of 10 inches. Notice that we're in inches, which is British, and we want to go to metric, which is liters here, okay? I'll remind you the volume of a sphere is 4/3 pi r cubed, okay? R cubed. I can find the volume, very easy, 4/3 pi, and then I'd have 10 inches cubed, and I can calculate that I could calculate it, whatever I want to calculate it as, right? But this will have 10, so, right, 10 to the 3rd power is 1,000, so I'm just going to write this number as this, inches cubed. That's a fine number. I'm not going to plug it in my calculator yet. I'm going to be working with fractions anyway, so I'm just going to leave it like that. And why I did this is to work with cubed units. I want to go from inches cubed to a liter, okay? So let's think about conversion factors here. I've written down a few so that we can use them. We're definitely going to have to convert from inches to a metric unit. And the easiest way to do that is to go maybe from inches to centimeters, right? And we saw that on the previous slide. Let's see, 1 inch equals 2.54 centimeters. That's a thing, okay? Another conversion factor that we will need, I wrote it down here, 1 milliliter equals 1 centimeter cubed. If you're a chem person, that's a very familiar conversion factor there. A milliliter is 1 centimeter cubed. So if we get from inches to centimeters, We can get from centimeters to milliliters, and then I'm going to note that 1 liter is 1,000 milliliters, right? So I wrote out my conversion factors here. I have my number, and so I'm going to do conversion with the ladder method. So I'm going to write 4,000 pi divided by 3, and this is inches cubed. And I'm going to put this across here. Okay, so I want to get from inches to centimeters. So if I write 1 inch down here, I can put 2.54 centimeters up here. And it may seem that easy, but notice that I put only one factor of inch here. And there's 3 factors of inches up here, right? I have to do a conversion not only on this dimension, but also this dimension and this dimension. There's 3 dimensions of length that I have to do a unit conversion on. So I could write these all out separately. I could do another 1 inch times 2.54, right? I would do this 3 times, but this is what I'm going to do is I'm just going to cube this number, and I'm going to cube this number. Notice if I cube this number, that gets rid of the inches cubed. That's an inch cubed. And then also that would cube the numerator. And when I do this, mind your exponents here. The cube gets distributed to both of those. Not only does the centimeters get cubed, but I have that 2.54. Remember, I need that 2.54 in 3 dimensions. So that 2.54 gets cubed as well. Okay? So that's the tricky part of that question. Let's see, we're in centimeters cubed, which means I can go 1 centimeter cubed is 1 milliliter. And then now that I'm in milliliters, I can say 1,000 milliliters is 1 liter. And I can go from inches cubed to volume in liters, which is what I was looking for. So let's see. I will double check my units just to make sure they cancel out. I have inches cubed and inches cubed. Those cancel. I have centimeters cubed and centimeters cubed. Those cancel. I have milliliter with milliliter, and I am left with liters. So I calculate this. I'm good to go. I have liters left over. When this is calculated, when you run it through your calculator, you get 68.642 liters. I'm going to go back up here and notice that there's only one significant figure in my original number. So when I return this answer, I'm going to have one significant figure in the answer, and so I get 70 liters. That would be the answer that I put the box around. V equals. So when you do unit conversion with powers of units, you have to take the conversion factor to that same power. That's the trick there. I picked out a problem involving moles, which is a little bit more towards atomic physics or chemistry. Moles is a common unit in order to work with number of atoms in a solution, etc. How many moles are there in 5 grams of NaCl? NaCl is common salt, table salt, right? Sodium chloride. Note that 1 mole of NaCl has a mass of 58.4 grams. So I'm going to write down the conversion factor here. 1 mole equals 58.44 grams. Is that going to be, if I want to go from grams to moles, I already have enough information. All right, so if I do this ladder here, I can just say that 58.44 grams is 1 mole. And when I multiply that out, actually divide, right? The grams cancel, and I'm left with mole. It'll be 8.56 times 10 to the negative second moles. Okay, so whatever a mole is, you don't even need to know what a mole is. You can just do a conversion here because you understand what unit conversion is. In the next part here, we'll need to know how many atoms are in a mole. How many atoms are in this much NaCl? So we have 5 grams, so it's this many mole. All right, and what I'm going to note is that 1 mole equals 6.022 times 10 to the 23rd. You may know about Mole Day in October, 23rd, right? October 23rd. This is the number of units of things in one mole. To me, it's like a dozen, right? You can have a dozen eggs, but you can also have a dozen children or a dozen apples, right? It doesn't matter what the dozen is, it's an amount, and that's the same thing for me is a mole. One mole contains this many things, right? 6.02 times 10 to the 23rd, which is actually a huge number, okay? So one mole is, when I think about salt, salt is a diatomic molecule. So if I have 8.56 times 10 to the 26 moles, I'm going to have that many diatomic molecules. And then what I'm going to note is they want to know how many atoms are this. Well, each molecule has 2 atoms in it. That's why I called it diatomic, right? It has 2 atoms in it. So I'm going to have to count the number of molecules, and once I get the number of molecules, then I can count the number of atoms, because there's 2 atoms per molecule. So I can write that out here. 1 mole will be this many molecules of salt, NaCl. And then I'm also going to note that one molecule of salt equals 2 atoms. So it says how many atoms are in this much. So let's do the conversion. I'm going to write down my original number and start my ladder here, mole. I have mole in the numerator, so I want to get it in the denominator. And I will go from moles to number of molecules. Notice that I can't go to atoms yet, right? I have to get the molecules. Once I know molecules, then I can get the atoms. So 1 mole is 6.022 times 10 to the 23rd molecules of salt. 1 molecule of salt, that's in the numerator now. I'm going to put 1 molecule in the denominator in order to get those 2 to cancel, which means that 2 atoms goes on top. 1 molecule has 2 atoms. That's the conversion factor there. Okay. So I can double check my units, do the dimensional analysis here in order to make sure that my units are canceling and I get the right units out. Yes, that's right. And when you do this, you get 1.03 times 10 to the 23rd atoms. You can do this in your calculator for yourself, but that's the answer. I'm going to make note to tack on my units on the end. I've not mentioned that, but make sure you're doing that. When you get your units, it's not just the number, it's the units as well. The last thing I want to talk about is dimensional analysis. And I just mentioned this word. What is dimensional analysis? For me, dimensional analysis is including units in a calculation and reducing them, like we had been in the ladder method, reducing them to ensure that the dimensions of the final value are accurate. Okay? So as you do your calculation, put the units in there and make sure they're canceling in the numerators and denominators, and how are they turning out how you want them to be the right unit for the quantity you're calculating. So I brought up an example here that's completely random. You might not even be familiar with the concept, but it's a rate of heat conduction. And this is the rate, Q over T, which is heat per unit time. That's what that stands for, which is a joules per second, heat per unit time. And that is the rate, right? A rate is per unit time. So the rate of energy, the rate of heat conduction out of the human body. And this is the equation for it. Kappa, area, temperature. Notice that temperature is in here and there's a distance in here. How far right? So when you look at all this stuff, there's units to all of these values. Kappa has units, area has units, temperature has units, the distance has units, and we want to reduce it down to joules per second, right? All of those have different units. So I picked this problem out here so we can look at it. There's a T1 and a T2, and even just fumbling around, you might be able to figure out this equation, right? If I want to calculate the rate, I'm going to have to take the kappa, which is the thermal conductivity of the material, that I'm working with, which is here human body, so human tissue. It says the thermal conductivity of human tissue is on average 0.5 joules times, whoa, that's a lot of units in there. Well, I'm going to just note that there's the kappa in the problem, and I'm going to put kappa in there, 0.5. I'm just going to write 0.5. That's good enough for that number. And then I'm going to put the units in here. There's a joule on top, and then there's a second times meters times degrees Celsius on the bottom. Okay. So when I multiply by all the other terms and start canceling out, I'm going to end up with joules per second. And I see a joules per second in here, which means that I need to get rid of the meters and I need to get rid of the degrees Celsius. Can I do that? Maybe. Let's see, area. There's an area term in here. Ooh, surface area. There's a surface area in here. Okay, so I have 1.4 meters squared. Oh, I'm going to notice that there's a meters canceling out, right? Only one factor, though. This has a meter squared up here, and this has a single meter here. So I'm gotten rid of meters, but I still have meters and the degree Celsius in here, and I need to, right? So when we're looking at these other terms, the difference in temperature, T2 minus T1, the core temperature, so it's going from 37 to 34, so that's 3 degrees Celsius that it is changing temperature. I'm getting excited because those will cancel. And then also we have over the distance that the thermal conduction is happening, which is 1 centimeter, which I'm going to know is 0.01 meters, right? And if I go back up here, I'll get a different color. So the degrees Celsius cancel, and then I have a different meter cancel. The first meter is in pink or purple and pink, and it canceled there, and then the second one's in blue, it canceled there. And so when I look at this, I'm really excited. All I have left over is joules per second, which is my target units, right? I'm not doing unit conversion, right? There's not really unit conversion going on. What I did was I took all the quantities and the units of those quantities and put them into that equation. And when I reduced, I made sure that the units reduced to the units that I was looking for. When you calculate this out, when you multiply all these things out, 1.5 times 1.4 times 3 divided by 0.01, right? I just pull the numbers out. I know they're going to have units of joules per second. This becomes 150 joules per second. That's what I would put a box around. And I know that's the right units, and I put the numbers in the right way because the units canceled out.